So there's really no indication that it's actually recording except that this turns red. So I'm trusting that I'm recording, and then I just have to listen to it later and hope that you can hear me. So unfortunately, I did check because some people answered questions in fourth period, but you couldn't hear them. So if you're all worried that someone's gonna hear you talking, unless I came right up to you with the microphone, I don't think it's good enough. So anyway, what we're going to try to tackle is we're going to try to look at number 18, number 20, and 27. So we'll start with 18. Key things I always try to pinpoint out of the problem is we want to get that initial velocity, so that 30.3 meters per second they have on there. And then I actually changed this a little bit from the book. The book just said that you wanted the golf ball to go the maximum distance possible. It didn't actually give you the angle. So I put on there for maximum distance, what we want to do is try to get as much of our velocity in the horizontal and in the vertical as we possibly can. Well, the best vertical would be to launch it straight up, but that's not going to go anywhere. And the best horizontal would be to launch it at 0 degrees. But again, then it's just rolling across the ground, and that's not going to be what we want. So if you think about it, 90, so what's the best between 90 and 0? Would be halfway, would be 45 degrees. So if you ever hear something say that you're going for a maximum distance, from a physics standpoint, that basically is saying that it's being launched at a 45-degree angle. Now, if you get really picky, my golfers know that it doesn't actually work that way. 45 is not the best angle. You actually want something slightly different because you would get some air resistance. If you actually watch it, you will find, depending on how much wind you have, is it's closer to around 40. You have to drop the angle a little bit to get a little more forward and not as much up. But for us, we're going to do without any air resistance, so we'll go after 45. So I've got 30.3, 45 degrees. And we're going to try to find how much time it spins in the air and what's the longest hole-in-one that they could make. 18. Let's draw this out a little bit. Here's my hole over there. It's going to be the hole-in-one. The golf ball over here. Put some dimples on it. There we go. So we're going to hit this golf ball. It's traveling at 30.3 meters per second, and it's traveling at a 45-degree angle. And the idea is we want this golf ball to go flying through the air, reach some maximum height, and land right here in the hole. Something like that. That was actually a horribly drawn one. Let's see if I can fix that a little bit. Trying to draw a parabola. I'm not the greatest at drawing parabolas. So. First thing I'm going to suggest on any of these problems, take that velocity and split it up into horizontal and vertical. It's just one of the things I think is very useful to do. So instead of actually thinking of it at 30.3 meters per second, let's figure out how fast this thing is going horizontally. So let's find its Vx. Let's figure out how fast this thing is going vertically. So let's find that Viy. So if I do that, you're going to run into this over and over again. Vx is just going to be your 30.3, your initial velocity, times the cosine of your angle. And Viy is just going to be your initial velocity times the sine. I do not want you to use radical form. I know from geometry, and yes, this is going to be weird, but I remember this all the way back to 9th grade geometry for myself, that the cosine of 45 degrees is root 2 over 2. Because we did the same stuff. We learned all those roots in 30, 60, 90s, 45, 45, 90 triangles. I don't want to leave it that way. So I always want to get a decimal approximation and calculate that out. So I've already solved this one earlier. So let's see, my calculator tells me that my Vx would be 21.4253. Whoops. 21.4253. It keeps going. There's some more decimals, but just get an idea. And then, if you do remember your geometry, what's true about the cosine of 45 and the sine of 45? They're the same. Very good. So don't even really need to recalculate this. Just write the same number. And that's one of the reasons why this works so well, why 45 degrees is such a good one, because you're getting as much of your velocity in the vertical and the horizontal at the same time. So it's because of that symmetry. So the things I want to know is, I want to know how long is this golf ball in the air for, and I want to know what's the maximum hole-in-one we can make without it rolling. So the idea is we're just going to plop it right in the hole. So we're after an X, and I want a total time in the air. Whoops. Now, for time, my suggestion is kind of what we did back in chapter 12. Problem number 12 and problem number 16 is I'm going to borrow some of the stuff we did on those. So going back in time, I always like to use the fact that when I'm at the highest point, I know my vertical velocity is 0. And if I use that, then I can actually take this VFY equation that equals VIY and solve for time, and I end up with this little equation down here. I use that for question number 12. I even used it for problem number 16, where we had our skateboarder go off the ramp. I used the fact that there's 0 meters per second at the top. Now, in this particular case, we used it to try to figure out how fast they were going and how high they went, but we could also still use it to find time. So I'm a big fan of using that. So I'm just going to kind of borrow that same idea, use the fact that its vertical velocity here at the top, its Vy is going to be 0 at the top. So our VFY equal VIY minus GT equation. This part's going to be 0. So these are going to equal each other. And I can find the time is going to be my vertical velocity divided by gravity. But that is just the time to go from here up to here. In other words, it's just the time to go up. So I'm going to add one extra word to that. I'm going to put T up. So that's a great equation for finding how much time it takes to get to the highest point. I don't want that, though. I want the total time this golf ball is in the air for. But if I have this thing going from here up to the top, and it doesn't say that it landed at any kind of difference in height, it actually is just looking for maximum. We kind of assume that the ground is fairly level. I know that's probably not a good assumption on a golf course, but for our case, let's assume that the fairway is level. We're trying to figure out this maximum distance. The time to go up, how would that compare to the time it takes to come down? They should be the same, because we have this nice little symmetry, and so the total time in the air is just going to be twice the time it takes to go up. Remember, this only works if you have that perfect symmetry. If we weren't talking about perfect symmetry, then it wouldn't work as well. For example, in this particular problem, if I was in 16 and I was talking about the skateboarder going from the top of this ramp all the way down to the ground, if I had tried to find that, then this wouldn't have been symmetric. This red line here is not symmetric around that top part. What we did, though, is we were just trying to find this little x and that height, and then we did actually use this little part that was symmetric. So if you can find that symmetry in there, it's useful. If you can't, then there's other ways you have to go about it. We have symmetry here with number 18, so we're good to go. Ta-da! Part A. I'll let you kind of finish out the calculations. That's usually my plan. Next part is, let's figure out how far, if I were to hit this golf ball and it went across level ground and went plop right into the hole, what's the farthest hole I could actually make? So I'm going to switch to blue, because I'm going to try to do everything. I mentioned this on Friday. I can't remember if I mentioned it with you guys on Thursday, but just kind of a little reminder is just to make my equations kind of make sense, is I'm going to try to keep everything horizontal with blue, everything vertical with green. Anything that's kind of a combination is going to be red. That way, kind of a color code, maybe it'll help kind of guide things. So now I'm after X. I want to know how far it is from launch to landing here. Well, our best equation for finding X is to take a horizontal velocity, which I have. Look at it. There it is right there. and just multiply it by a time. Now, in this particular case, since I want to know how far from launch to land, this time has to be the total time in the air. When we did this in problem 16, we actually used the time just to go up because we were just trying to have them go from here to the highest point. We were just trying to find that displacement. So for part B, you basically have answered everything already by doing part A. You found the time that took in the air. We've already calculated Vx because my suggestion is always to find that, and boom, boom, we got it. Now, as a side note, there is another equation that I find that a lot of people like to use. Jump back to my equation sheet, and it's this equation right down here. It says gx equals 2 times vi squared times cosine theta times sine theta. It's actually one of the red equations. So I'm going to write that over here. And I modified it a little bit before I had everything erased. G is actually a vertical information, and X is a horizontal. So some people see that and they're like, hey, there's an X. I've got VI. I've got the angle. Is there a way I could use that equation? And you can use that equation. It's really nice. In this particular case, you can actually take your gravity. This isn't going to work, but I'm going to try it anyway. Yep, it didn't work. Sometimes I can highlight just one little thing and move it, but unfortunately it's grabbing the entire equation, and I don't want to move the whole equation. See how I can move the whole equation? But I don't want to move the whole equation. I was just trying to move the G. So anyway, if I take that and I divide by this gravity, so if I divide by gravity over here and divide by gravity over here, divide by gravity, I have a great little way of finding X. You just have to understand what this X actually represents. We talked about this a little with problem number 16. This X is how far it is to go from one point to another point that's at the same level. In other words, it has to land at the same height it was launched from. This would actually solve for part B, because the golf ball is going from here to your hole in one. So this is actually what this equation was kind of designed for, a question like number 18. Things to kind of watch out for, things to kind of notice. You basically did that already. Notice it has a factor of 2. Where did that 2 come from? It's what we used up here for the total time in the air. It's got vi squared, but I know vi squared just means vi times vi. So I'm going to split it up. I've got a vi times cosine theta. Hey, isn't that just what vx is? And then I've got a vi times a sine theta. Isn't that what VIY is? So in essence, what I've got on the top is I've got 2 times Vx, awesome, times a VIY. Well, my time in the air was equal to VIY. So really, when I did this, I did actually take Vx times VIY, and then I just divided by gravity. Hey, there's gravity. So really, I did the exact same thing. By doing this in 2 steps, this just does in 1. So it's just another way of looking at it, as long as you kind of understand where everything's coming from. Ta-da! Another lovely little projectile problem. This is kind of one of the problems that you're going to get on the test on Thursday is going to be something similar to this. You're trying to find how long is it in the air for? How far does it go? The other possibility is, like we saw in number 16, is maybe you want to know how high did it go. So those are one of the problems is going to be finding something along those lines. So if you kind of understand 12, 16, 18, you're definitely set. Okay, move on. And if you're missing part of this, feel free to ask me and I'll come back to it, or you'll get to see it later. Next up is 20. So 20 throws something new at us that we didn't have before. It looks like 16, but it's got a little bit slighter. It's another golfer. So the idea is this time the golfer is going to shoot onto the green that's elevated 3 meters above the point. So maybe they're doing a little chip shot onto the green, whatever. So we've got this little displacement of 3 meters above the point where the ball is struck. 3 meters above, that kind of sounds like some kind of vertical displacement. So I'm thinking of it maybe as a Y. We'll see what happens. It's going to leave the club at 14 meters per second at an angle of 40 degrees above the horizontal. So we've got an initial velocity at an angle. It reaches its maximum height, then falls down to the green. Ignoring air resistance, find the speed of the ball just before it lands. So that's something new as well. We haven't been finding like a speed. So we'll have to kind of see what we've got. So I like 20. It's a little bit different than everything else. Let's see if we can get a setup here. So I've got level ground for a while, but there's some section that is higher up. So they mentioned that they're going to chip it onto the green, which is 3 meters above this point. So this is 3 meters. So if I kind of visualize what's going on here, I've got my golf ball here. We're going to launch it. Whoops, it's supposed to be red. Going to launch it at 14 meters per second at an angle of 40 degrees. So the idea is it's going to go up in the air. It's going to reach its maximum height somewhere. And then it's going to fall into the green. So it has some kind of motion like this. Unfortunately, not a perfect parabola. So we don't have that perfect symmetry that we had in the previous problems. But the nice thing is hopefully we won't even need it. And what I'm after is actually I want to know what speed does it land at. So what I'm looking for is when the golf ball hits the ground up here. So I want to know what this final velocity is. And once you kind of understand you're trying to find a final velocity, I think you'll be on the right track. However, just like we saw when we did some horizontal projectile problems, and one of your problems on the test will be a horizontal projectile problem. And I mentioned this in first period. Really, if you can do what we're doing now, you can do a horizontal one again. We did it way back at the beginning of this chapter. But remember, horizontal just means that the angle is 0 degrees. So if you think about it, the cosine of 0 is 1, and the sine of 0 is 0. So your VIY is 0 for all of those, and all of your velocity is horizontal. So in essence, you can do kind of the same stuff. So we're going to try to figure out this. But I want us to go back to what we've been doing and realize that this velocity can be broken up into a Vx and a VIY. In other words, how fast is this golf ball going up and how fast is it going forward? So just pull out my stuff up here. VIY would be 14 times the sine of 40 degrees. And then Vx is going to be 14 times the cosine. Hand it in the calculator. I've already calculated these, so I thought this one was kind of neat. The sine happens to come out to be almost 9. So it's 8.999 meters per second. So in essence, even though they hit it at 14 meters per second, it's basically going up at about 9 meters per second. And then forward, horizontally, it's going about 10.7246. So here's one of the things that's going to be useful for us. If I hit this golf ball at this 40-degree angle, it's going to go flying through the air. It's going to reach its maximum point, and then it's going to start coming down. If it actually came all the way down to the same level it was before, this question would be really easy. In other words, if it landed on the ground that was at the same level or on flat ground, it should hit at a 40-degree angle at 14 meters per second. In other words, its final would be identical to its initial. But since it lands somewhere higher, that's not quite the case. But there is one part of it that is actually very important. What's true about the horizontal acceleration? There isn't any. So no matter where the golf ball is, it's always moving forward with exactly the same velocity. So when it gets over here, it's still moving forward. Its Vx is still the same. It's still moving forward at 10.7246 meters per second. That's not the final answer, though, because what I want is Vf. In other words, I want this, and that Vf is made up of two things. It's made up of how fast it's moving horizontally, which we know. What else is it made up of? A vertical part. So I got to draw a green one on there. There it is. It's going to have some little VFY. Now I always like to take that VFY and slap it over here so you can kind of see that together these make a nice right triangle. And so what I'm really after is VF. So VF is going to be made up of these two things. But before I can solve this, I got to figure out what VFY is. So now think about the information I have. I know VIY. I'm assuming they're golfing here on Earth. So I'm going to assume that gravity is 9.8 meters per second squared. We're not going to go to other planets until we get to chapter 5. So I just keep saying that, but that's because eventually we'll look at those. This 3 meters, that's got to be useful to us. And it is, because the golf ball started here and it finishes 3 meters above where it started. So this 3 meters is actually a y. It is a vertical displacement. Just like if it had landed at the same height, we would have said y was 0. But since it's landing somewhere higher, it's positive 3. What if it landed it down the hole? What if the green was lower than where you started? Say it again? It would just be a negative value, exactly. So this is truly our y, so that's great. So I need an equation that's got VFY, VIY, G, and y in it. In other words, it doesn't have time in it. And so if I look at my lovely equations, one more. Everything under the vertical column has time in it except for this bottom one. This is a really useful equation when we don't know time. It says that VFY squared equals VIY squared minus 2GY. Hey, look at that. It's even set up to solve for VFY. We should be set. There we go. So to find this VFY over here, we should be able to do it by saying that VFY squared equals VIY squared minus 2GY. Now, things that we did this before, but this one's a little bit different. VIY is not 0. It's 8.99, so we've got to put that value in there. G is our 9.8. Y is a positive 3, but we're still subtracting it. The subtraction is coming in the fact that gravity is downward, but we don't have to put a negative 9.8 because we're already doing that. You're going to solve this for VFY. That'll be this answer. Most common mistake is people are like, oh, I'm done. That's my final velocity. But it's not, and that's why I was trying to remind you that what I really want is this diagonal. I want to know what this velocity is. How do I find the hypotenuse of a triangle when I know two sides? I pull out, starts with a P. Pythagorean Theorem, yes. In other words, VF, whoops, it's supposed to be red. Here, come over here. You're too far away. VF squared, the hypotenuse squared, should equal my VFY squared, my vertical component, plus my horizontal component squared. So this is just our nice little Pythagorean theorem. I actually have this on the equation sheet because we used it when we were doing horizontal motion. But trying to find that final velocity, you just need the final in each direction. Your Vx is always the same, so that one wasn't too bad. We just had to find that VFY. Ta-da! Another lovely problem. I typically, since we saw this a little bit with our horizontal motion, and now we're seeing it a little bit here, I have often done at least one part of a problem where you do have to find a final velocity, but not always. So 20 is okay. It's not my favorite. The thing I do like about it is the fact that you do have a y in here, so you have to use a little bit with that. But I think this would have been a good one to find like a time. We could have used it to find time, maybe find how high it went or how far it goes until it lands on the green. Any of those would be good, but just an extra little tidbit that we have in there. Questions on 20. I got one more. You ready for one more? 10:09. I think we're good. Okay. The next one talks about a fire hose being ejected at 35 degrees at 25 meters per second. Hey, look at that. We've got VI. We've got angles. We're good to go. The water is leaving it. We're assuming it acts like a projectile, and that's one of the things that's cool. If you've ever shot water out of a hose, it actually moves very similar to a projectile. And they want to know how far from a building should the fire hose be located to hit the highest possible fire. Now, firefighters probably know this instinctually. They just go, oh yeah, I'm going to try to hit that, fire on the second floor. We're going to stand here, how you should hold it. So probably just instinctually they know it. We could do this by trial and error. You could just be tilting it up and moving back and forth till you got to the right spot. What we're going to try to do is see if we can calculate it. So if I'm going to try to calculate this, I'm going to grab the information I have. I have a speed and I have an angle in here, 25 and 35. Let's see if I can draw this out. Put a building on here. There's my building. And the building's on fire, so we need some flames. I determined I needed a little bit of orange in there. Get some orange in our flame. There we go. Maybe throw a little bit of yellow in there. Perfect. So the building's on fire. So we come in. We're a firefighter. We got the hose. Goes the hose all the way back to the fire truck somewhere back here. And we're going to shoot water out of here. So the water is going to come out. We know that it's going to leave the hose at 25 meters per second. And we're going to tilt it at a 35-degree angle. What we're trying to do is we're trying to hit the highest possible fire. So if I think about this motion, we know that this water is going to act like a projectile, so it's going to travel nice little parabolic motion. What we want is we want the water to be at its highest point by the time it hits the fire. What do we know about the velocity of something at its highest point? We know that it has 0 vertical velocity. So in essence, they're sneaking that part into the problem. That VIY would be 0 because we're at the top of our motion. So let's use that to our advantage. If it helps, we could actually call that VFY because it's just going to be the final. We're only going to the building. We're not having the water go past it, or we don't care what happens afterwards. Other things I'm going to do, just like I've been doing, let's take this velocity, let's split it up into how fast it's moving horizontally. Let's figure out how fast it's moving vertically. You know the drill, so let's find VIY. That's going to be 25 times the sine, 35 degrees. Make sure you remember, and I usually do this, just for my math classes in the past, is I always remember x kind of goes with cosine and y goes with sine. So if you kind of remember that those match up, then I think you should be pretty good. I've already got these numbers. So horizontally, this thing is going about 20.5 meters per second. And vertically, it's going a little over 14 meters per second. So the problem really wants to know how far away from the fire or from the building should we be. So how far away is not like the diagonal. We don't want the path along the parabola. What we're looking for is how far horizontally is it from here to the building. So we're looking for x. That's what we're after. To find x, same thing I've been doing. My suggestion is let's figure out Vx, let's figure out time. So we're going to take those two lovely things and multiply them together. Hey, look at that. We've got Vx. Yay, we're halfway there. We just don't have time. But we've done problem number 12. We've done problem number 16. We've done problem number 18. All of those involved time in some fashion, and one of the things that was really cool is we needed the time to go up, or we needed the total time in the air. For this one, what do I need for this time right here? I just need the time it takes to go up. So this t here is actually going to be the time it takes to go up to the fire. In other words, to get to that highest point. In other words, where VFY is going to be 0 from this VIY of 14.339. So this ends up being, we've done it already a couple times before, so I'm just going to jump straight to the final result. That the time it's going to take to get to this highest fire is just going to be the vertical velocity divided by gravity. Really what's happening is, if you think about it, gravity is 9.8 meters per second squared. It tells me every second that it's slowing down in the vertical direction by 9.8 meters per second. So really what I'm doing is I'm saying, okay, I initially launched it at 14.339. Every second you're taking 9.8 meters per second away. How much time did it take to get down to 0? If you launch something at greater than 9.8, it's going to take more than a second. If it's less than a second. If it's twice as much, so you can actually get a good estimate right away. So borrowing this again, remember, this is just this equation, VFY equals VIY minus GT, but where VFY is 0, these two equal, and ta-da, we have time. I really like this problem. I even had one very similar where instead of a fire, you were trying to, I don't know if anybody's ever tried to do this. I know I've had people try to do this. If you ever tried to throw like something up to somebody that's in a building or in a house that's like on the second floor or something. I've had people go out here on their little parking lot and then try to throw something to somebody in the window in our building, and they always do a horrible job. And I always go, you could calculate that, and they're like, yeah, I'm not in physics. So because it's usually some random person, and then people will have the windows open because it's too hot in here, and someone will be like, hey, Timmy, and they'll try to throw something to him. I let them do it once, and I said, okay, you got to calculate how high is the building, and how fast do they have to throw it? What angle are you throwing it at? And the kids didn't understand where I was going from, but that's basically what this problem is. It's a great little problem. Why would you want it to be at its highest point when it gets there? I think the best reason why is because your velocity would be 0. It's the same thing like if you're going to catch a foul ball at a baseball game. Wouldn't you want to be high in the stands so you're kind of pretty close to the top of its motion? It would actually be going its slowest because it's not going to be moving. It's still going to be moving horizontally, but it's not moving vertically anymore. So you see those times where it goes way up in the stands and someone just kind of catches it with their hands. You're like, hey! And you're like, wow, that would hurt. Well, sometimes, yeah, but if you catch it high in the stands, it's not bad. Now, if you're down at like field level, then those foul balls, and you're like, I don't think I'll catch it. You want to make sure you have the gloves. So. Okay, thank you for bearing with me and looking funny with the thing.